Welcome back. In this video, we'll consider the evaluation of the definite integral. This will be the first video on definite integrals. And this time around, we are starting off with the integral around the unit circle. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. In the last video, we considered the indefinite integral, and we saw precisely the process for carrying out that integration. But this time around, we start off with the integral in the unit circle. This time around, the functions will be such that they would usually tend to be trigonometric functions, basically because of the angles that ranges between 0 and 2 pi rad. Because of this, we know that from 0 to 2 pi rad, you have yourself a circle. That is the angle at the point. And that is essentially what is being referenced here. Usually, we would be transforming the functions that we would be given by using the exponential form of the complex number about the unit circle, which means where the radius is equal to 1. That is, we'll be using z equal to e raised to power I theta at all times. You would see exactly what this means when we, of course, start taking examples. But first and foremost, let us write our modus operandi. First and foremost, we are talking about the integrals of this form. There is a bound, hence why we call it definite integral. And then we have f of theta d theta, where, of course, usually f of theta usually refers to functions in terms of usually either the cosine function or the sine function, usually, right? So this evaluation will be done. And then the transformation is, of course, of the form z equals e raised to power I theta. Of course, r is equal to 1 because we are talking about a unit circle, which means it will have itself a unit radius. So let us now see how exactly this plays out when we put into practice a question. Now, before we do so, we remember that the cosine function and the sine function has some very, very pleasant complex number combinations. Remember, we looked at it when we were considering the ways in which we could expand different analytic functions. So we can say that we remember that cos theta can be written, of course, as e raised to power I theta plus e raised to power minus I theta divided by 2, which, of course, is going to mean z plus 1 over z divided by 2. So that means I can write cos theta as 1 over 2 into z plus 1 over z. In one of our videos, we considered this transformation in detail, so you can take a pause, watch that video so that you have much more clarity. Similarly, on the same vein, we can say that sine theta this time around, which is the imaginary part of the polar form, will now be 1 over 2i z minus 1 over z. These are standard identities which we generate for the polar form of the complex number. Now that we have this, we can now go and proceed towards taking a question to clarify exactly how this evaluation will go. As always, we will choose a question that is very, very rigorous so that you have clarity of the process and can help you solve any and every single kind of question that you have. So let's start. In this case, so this is the integral. We have to evaluate the integral from 0 to 2 pi of cos 2 theta divided by 1 minus 2p cos theta plus p squared d theta, of course. And then we have a special range of values for p, which is from 0 to 1, open on both ends. So 0 less than p less than 1. So the very first thing we do is, of course, we want to transform as much as possible such that we can rewrite this as a function of z. That is essentially what this transformation is all about. Remember that being able to write it as a function of z would allow us convert it to the integral on the entire contour, right? If this is the integral over the unit circle as represented by the bounds, then it means if we transform to the function of z, it becomes the integral over the entire contour, as the case is. So let's carry out the process of transformation step by step. First off, We remind ourselves that z is equal to e raised to I theta in the unit circle, which would immediately mean by subject of the formula that theta will be equal to 1 divided by I ln z, right? The logarithm of both sides creates ln z, and then dividing by I gives us this. Of course, we can also proceed to rationalize if necessary, but we'll hold on that for now. Now, from this representation, the goal is to find the value of the theta. So if we differentiate easily, we have that the theta would simply now be equal to 1 over zi dz, right? Because 1 over I will be a constant. Differentiation of ln z will give us 1 over z. And there we go. So now we have the value of the theta. The next thing is now to find representation for cos 2 theta as well as cos theta. Do not forget that we already know that cos theta is equal to 1 over 2 z plus 1 over z. So we can use this representation to determine what the value of cos 2 theta would be. Now, by multiple angle formula, we have that cos 2 theta can be written as 2 cos squared theta minus 1. This is a very, very interesting identity. This would immediately mean that we can write this, of course, as 2 into 1 over 2 z plus 1 over z squared minus 1. This is what we have. Now we can proceed to take the LCM of the inside before we square off. And if we do so, it means we'll have 2 into z squared plus 1 divided by 2z all squared minus 1. Now, simplification of this process, the denominator breaks down to 4z squared, cancels out the 2 outside, so you can easily have z squared plus 1 all squared divided by 2z squared minus 1. You can also proceed to take LCM so that at the end of the day, cos 2 theta after expansion and LCM would simply give us 0 to the power 4 plus 2z squared plus 1 minus 2z squared divided by 2z squared. So this simplifies to 0 to the power 4 plus 1 divided by 2z squared easily. Now, from here, the next thing is we have already gotten a representation for the numerator. Let's now proceed to do the same for the denominator. In the case of the denominator, what do we have? This time around, we realize that for the denominator, we have that 1 minus 2p cos theta plus p squared can indeed be written as, bring the values without theta together, we can have 1 plus p squared minus 2p cos theta, which of course we can use this and would have, we can also decide to take the LCM if you like, but in the case we would have z squared plus 1 divided by 2z. This is the representation we'll have. And then we can bring it all together. We'll have 1 plus p squared minus p into z squared plus 1 divided by z. There we go. Now from here, we can take a general LCM. So we'll have z plus p squared z minus p into z squared plus 1 divided by z. Now we can see that minus p squared z here, or plus p squared z here, and z here, of course, will be coefficients of z. And then minus p will be coefficient of z squared, and then minus p would be a constant. So we can rewrite based off that representation and have minus pz squared plus 1 plus p squared z, then minus p, all of which is divided by z. And that would be the representation of 1 minus 2p cos theta plus p squared. Brilliant. Now we can utilize this without spending too much time on much more complicated simplifications. For now, we can use this to change the integral, and that is what we are going to be doing on the next page. So while we turn the page, you can take a pause, try to work out the mathematics of this, and see if it matches what we are going to have on the next page. Now, to make it simple, so that we don't have to repeat ourselves, we can say let I be equal to integral from 0 to 2 pi of cos 2 theta divided by 1 minus 2p cos theta plus p squared d theta. So from here, we can easily see that I will now be equal to, let's make our substitutions as clearly as we can. And so from our substitutions, we would easily see that because we were integrating the unit circle on theta, this time around on z, it would now give us the entire contour, right? And then cos 2 theta, which we have gotten earlier, would now be 0 raised to power 4 plus 1 divided by 2z squared. And this is going to be divided by the denominator, which we have, of course, gotten as minus pz squared plus 1 plus p squared z minus p divided by z. Now, this would represent the fraction, and then the theta, do not forget, we have evaluated the theta as 1 over zi dz. So, let us, of course, turn this function, remove the division sign. We are now going to have this to power 4 plus 1 divided by 2z squared multiplied by z divided by minus pz squared plus 1 plus p squared z minus p, and then you still have 1 divided by zi dz. From here, easily we can see that z here cancels out z here, and then we see that the numerator and the denominator will not easily cancel as planned. From here, we see that 2 and I in the denominator are constant, so we can bring them out. So we have 1 divided by 2i integral over c of 0 raised to power 4 plus 1 divided by z squared into minus pz squared plus 1 plus p squared z minus p, and then you have dz. Now, if we are having this form and we want to factorize this, the reason why we have to factorize this is so that we can identify the poles present in the denominator. Of course, we can easily see that by setting z squared equal to 0, z equal to 0 is a double pole. That is fine. But in this quadratic expression we have here, we have to simplify this, factorize if possible, to see if we have factors that we can make poles. Now, how can we do this process? We can simply do this process or utilize this process by a simple representation of completing the square. Now, how do we do this? We simply go to the entire process. The very first thing is factorize out the coefficient of z squared, right? And then once you have that, the next thing is to divide the coefficient of z by 2 and then square the result. Make sure it balances out by subtracting what you have. And then from there, simplifying the process. Now, we would do the first bits of business for this so that you see exactly what it means. If we factorize out the negative p, we are going to have minus 1 over 2i. The negative can come out completely. And then we have integral over c of 0 to the power 4 plus 1 divided by pz squared. And that's what we are going to have, pz squared. And then from having pz squared immediately, we see that inside now reduces into a factorizable expression, which will now have z minus p, z minus 1 over p dz. This is what we are going to have. So this is very, very interesting, right? And this is made possible because we have factorized minus p, which was the coefficient of z squared. Now, if you expand this, you see that you have exactly the same thing. For instance, expanding would see that the constant would be minus p times minus 1 over p, which would be plus 1. And then plus 1 times p will give you plus p. You bring the minus back, you get minus p. Balanced. Here you have z times z, that's z squared, times p, that will be p z squared, times minus, that will be minus p z squared. The same thing happens on the coefficient of z as well. So this is a balanced complete square. From here, we can now find the poles. If we set the denominator to 0, which of course in this case will be setting pz squared z minus p z minus 1 over p to 0, we can easily see that z would be equal to 0 as a double pole. As we said earlier, z would be equal to p as a single pole or a simple pole, and then z would also be equal to 1 over p. also as a single pole. There we go. So we have ourselves 3 possible poles as necessary. Now, from here, the next important bit of business is, now that we have gotten these expressions as the case is, we must now proceed to determine which of these poles would be valid within the region. Now, remember that the question as set is that we should consider the value of P that is between 0 and 1. Now, if we look at that, what does that mean in case of this question? We will say that since 0 is less than P less than 1, right? And of course, we are working within the unit circle. And within the unit circle, what do we have in the unit circle? We have that in the unit circle, absolute value of z is equal to 1. That's the maximum of the radius that can be found there. Then it means that when we take z equal to 0, for instance, that would imply the absolute value of z is equal to 0, that is less than 1. So this falls within the region. When we take z equal to p, we take absolute value of z would be equal to p, right? And this would be less than 1, right? Because in this case, do not forget that we have said 0 is less than p less than 1. So that's fine. However, when we take z equal to 1 over p, then absolute value of z would be equal to 1 over p, and this would be greater than 1. So this is out of the region. Because if we say p is less than 1, then 1 over p would mean the reciprocal of this function. So the sign would change in the middle to become greater than. So if p is less than 1, then 1 over p would be greater than 1. So it means that this last pole will not form part of our calculation of the integral via the residue, right? So now we have this representation present. The next thing is for us to now find the residue. Now remember, we are looking for the residue of this function, so let's call it a variable so that we don't have to stress. So let phi of z be equal to z raised to the power 4 plus 1 divided by pz squared z minus p z minus 1 over p. Here we go. Now, based off this, we know we have just these first 2 points to consider. At z equals 0, the residue of phi of z at z equals 0 would be, because z equals 0 gives us a double pole, so we have to apply the formula, be 1 over 2 minus 1 factorial limit as z tends to 0, the first differential of the function, right? So we have z minus 0 squared phi of z. Now, in this case, this is going to be 1 here. So you have limits as z tends to 0 of the first differential of, we see that this is z squared, so it cancels out z squared in the denominator. So we are left with z raised to the power 4 plus 1 divided by p into z minus p z minus 1 over p. That's what we have. Now, of course, we are going to differentiate. This is going to be in terms of the quotient rule. So if it's going to help us a bit if we expand the denominator so that we would easily be able to differentiate. So we can expand that denominator basically as pz squared, right, minus 1 plus p squared z plus p, right? And if you're confused, take a minute to expand this. The first 2 brackets will give you z squared minus 1 over pz minus pz plus 1. Now, minus 1 over p minus p, if you take the LCM, is going to give you minus 1 minus p squared, right? So if you factorize minus out, you have minus into 1 plus p squared. Then if you multiply with this p outside, you are going to definitely have this. So from there, we take the limit as z tends to 0 and differentiate this. We see that the numerator, which is vdu, which will be pz squared minus 1 plus p squared z plus p, right, will be multiplied by 4z cubed, that's v du, and then this is just the first part. You have minus u dv, which will be 0 to the power 4 plus 1, then multiplied by the denominator, which will then become 2pz minus 1 plus p squared. And all of this would be divided by the square of the denominator, which is pz squared minus 1 plus p squared z plus p all squared. Now, from here, we can simply evaluate and see at 0. Why can we do that? Because we know what would have made it undefined at 0 has already been cancelled out. So if we evaluate at 0, we can easily see that here, the denominator reduces to just p squared, right? Because this and this will vanish because of the existence of z. If we look at the numerator, we see that this and this would vanish. This would also vanish, so it means this entire part will vanish because you are multiplying by 0. But here, this would vanish, so you left with minus 1. And then here, you left with minus 1 plus p squared. So minus times minus will cancel out. So you're left with 1 plus p squared. In the first case, so it means that the residue of phi of z at z equals 0 is in fact 1 plus p squared divided by p squared. So that gives us the first residue. Take a minute, look at the process of solution. So you can see that this is actually very, very straightforward and valid. The next thing is to now find the residue at z equal to p. That's the second pole that is valid within the region of consideration. So we see that not all the time would we have to specify based off the value of the radius. Sometimes it can be based off one of the variables within the question. Let's go on. At z equal p, this time around, we can evaluate that the residue of phi of z at z equal p would simply be, because z equal p gives us, in this case, a simple pole. So we have limits as z tends to p of z minus p multiplied by z raised to the power 4 plus 1 divided by pz squared z minus p z minus 1 over p. Of course, that's the value of phi of z. So from here, we can simply evaluate this as limit as z tends to p of 0 to the power 4 plus 1 divided by pz squared z minus 1 over p. Now, if we put in our value, we'll see that this evaluates into p raised to the power 4 plus 1 divided by p cubed into this representation, which is p minus 1 over p. Taking LCM will cancel out one of these guys. So we have p raised to the power 4 plus 1 divided by p squared minus 1. And this would be value of residue of phi of z as z equals p. So now we have both residues that are valid within the question, right? Based off the region of focus. Now that we have this, the next thing is now for us to evaluate what the integral would be. Do not forget that the entire integral, which is I, is dealing with this, and this function has been called phi of z. So we'll make use of that notation as well. So it means that I is now going to be equal to minus 1 over 2i integral over c of phi of z to z. This is what we are going to have to evaluate. And do not forget that by the Cauchy residue theorem, this will simply be minus 1 over 2i multiplied by 2 pi I into the sum of residue, right? And when we take the sum of residue, it means at both regions which is valid, which is at z equal to 0 as well as at z equal p. This is going to be 2i can cancel out, so we have minus pi into the two values, which is 1 plus p squared divided by p squared plus p raised to the power 4 plus 1 divided by p squared minus 1. This is what we have. Now, based off these two instances, we can easily see that the factorization becomes, or the LCM, becomes very, very valid. So, here we would have that I would simply be minus pi into p squared plus 1, which is this guy, multiplied by p squared minus 1, and of course, plus p raised to the power 4 plus 1 divided by p squared minus 1. Now we see that this first part gives us a difference of 2 squares. we have minus pi into p raised to power 4 minus 1 plus p raised to power 4 plus 1 divided by p squared minus 1. So we see we are left with 2p raised to power 4 here. P raised to power 4 can divide p raised to power 2, or p raised to power 2 can divide p raised to power 4. And then we'll be left on top with minus 2 pi p squared divided by p squared minus 1. And if you do not want a negative outside, you can write this as I is equal to 2 pi p raised to power 2 divided by 1 minus p squared. And there we go. So this shows us the full process of finding the integral around the unit circle. The very first thing is we first and foremost calculate the transformation so that we can change the unit bounds into the entire contour. Then we evaluate based off the Cauchy residue theorem, because that makes it extremely easy for us to solve it. By applying the Cauchy residue theorem, we see that we just have to figure out which of the poles fall within the region and then evaluate the residue at those poles. Then apply the Cauchy residue theorem to add the two values together, multiplied by 2 pi I and multiplied by whatever values are outside the integral, which is what we did. So from here, we are able to easily solve and see that the result of the evaluation of our integral will simply be based off this concept, right? And this is very, very interesting to see, right? It is a very important note as far as solving this question is concerned, that first and foremost, as we have said, the integration of the unit circle will usually involve trigonometric functions, usually the sine or the cosine. The goal is always to use the transformation z equal to a raised by I theta to solve. I hope this has been very, very clear. If there are, of course, any questions as regards to any bits of our solution, please do send us a message in the comments so that we are aware of what exactly is the issue. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.